Hey everyone, welcome to the third video of section 2.4. In this video we're going to go through more differences between linear and nonlinear equations, including some of the terms used to talk about answers and solutions that really don't make sense in one form or the other. So we'll do that and give us some examples of how these things sort of work. Let's go ahead and jump on into that. So other differences between linear and nonlinear. First, what we're going to talk about is the idea of a general solution. So for linear equations, we have this idea that I get a solution that has a c in it, a constant, and using that c, I can get any solution I want to the ODE. Up to picking that constant c, I have found every solution in the form of something plus c or something times c, something like that, depending on what your actual formula is. For nonlinear equations, this is nowhere near the case. There might be times where you can, for a nonlinear equation, get a solution that contains an arbitrary constant, and with any constant you get a solution, but it's also quite possible that is not even all the solutions to your problem. That there are more solutions to your problem than just those picked by one constant. It's a possibility that you can choose that constant, but no matter what you pick, the value at 0 is always 1. Always, no matter what. And so you obviously haven't found every solution with that constant, but you found a bunch. So for linear equations, we have the arbitrary constant that always gives us all the solutions. For nonlinear, that may not be the case. And this is so much of an issue that we generally don't use the words general solution to talk about nonlinear equations. That's not really a thing that we end up doing because it usually doesn't make any sense. It doesn't really work. There's no real way to talk about it. So we generally just ignore that fact. We don't say anything about the words general solution. We'll talk about things that involve constants, but we won't use the phrase general solution for nonlinear equations. So the second issue to deal with is that of implicit solutions. So for linear equations, section 2.1, we had an explicit formula. It exists and it's always there. So linear always have explicit. And this is the y equals the 1 over mu of t integral of stuff. I don't care about the formula. The fact is there is a formula and it exists, and it always solves for y in terms of t. So we always have explicit solutions for linear equations. For nonlinear, again, not necessarily the case. Sometimes the best we can hope for is an implicit solution for nonlinear. And by that, I mean something of the form capital F of t y equals 0, and y so that y solves the ODE. Y prime equals f of t y. So this is sometimes called an integral of the differential equation if it's an implicit solution like this. And sometimes that's really the best you can do for nonlinear equations. There might just be no hope for anything better than that. You saw it a little with separable equations. You'll see it more with exact equations when we get there in section 2.6. But this is good enough usually. It's not great. You'd like it to be explicit, but that's not necessarily always possible. So sometimes you got to deal with this and live with it, and this is the best you can do for your answer. The graphs of this for maybe different constants or something are integral curves. We'll still talk about integral curves for this, but it's still an implicit solution, and it's not. You just have to deal with what it is. Sometimes you can't get nice answers, and this is what you just get. In this case, when we're in this implicit case, numerical solvers become very helpful in this case. And why is that? Because they can graph these really easily. It's easy to graph. You just throw it in Maple. This is the implicit plot command. And you just do this. It'll graph it for you. It'll give you a bunch of curves, and you can see what the ODE is going to do, even though you can't solve for y in terms of t explicitly. You only have this implicit solution. So this gives you an easy way to give you sort of a sketch of what it's going to look like. It can also do approximate solutions. Just by numerical stuff, you can get approximate solutions. So that's why these solvers become really helpful. The Maple and other, you can do stuff like this in MATLAB too. We're not going to focus on MATLAB because Math Heart wants me to use Maple, so we'll use Maple. But you can do things in MATLAB and other languages like this too. So in this approximate solution stuff will be more numerical methods. We'll talk about that right after the first exam. So that's going to be sections 2.7 and then chapter 8 where we talk about numerical methods for solutions that aren't graphical. They're numerical methods to actually get solutions. And then solvers can handle that too and give you approximate solutions to your problem right from the equation itself without having to do too much other work. All right, those are the points I wanted to hit this video. The next one we'll touch on section 2.8, which is a lot more theoretical and not really too important, but I'm going to spend one video on it just doing some vague stuff about what's going on in the section to give you an idea of what's going on there. All right, thanks for watching, and I'll see you in the next one.